I'd now like to talk about the basicity of anilines. Now, up to now, we've been looking at what happens when something releases H+. We're talking about its acidity. Now, with basicity, it's the opposite. We're looking at its ability to take in or accept H+. Now, we're going to talk about this in terms of its pKb and its pKa. And we do have a link between the pKb of the base and the pKa of the conjugate acid, and that is as follows. pKa of the conjugate acid plus pKb of the base is equal to 14. Now remember, to get a conjugate acid, the only thing you have to do is add H plus to the base, and that's how we make a conjugate acid. Also, we can make a conjugate base by removing H plus, but what we're interested in here is just how we make the conjugate acids. Now what I want you to do is compare the basicity of these two compounds here. We've got a standard amine and here we've got aniline. Here's what I want you to notice. Look at the pKb of the standard amine. You'll see it has a pKb of 4.0 while the aniline has a pKb of 9.3. And what I've said earlier was that the lower the pKb, the stronger the base. And what we notice here is that this is going to have a much greater strength of attack on the H plus than this one will. Now the reason for that is because of the lone pair here. The lone pair is pretty much stuck on the nitrogen, and it is therefore a fairly strong source of negative charge. On the other hand, with aniline, here's what we notice. The lone pair on the nitrogen is interacting with the electrons in the benzene ring, and that tends to make these electrons less available to attack an H+. Therefore, we have a lower basicity on the aniline than we do on the standard amine. Let's take a look at the strength of the conjugate acids. As you can see, the sum of each of these is 14. 4 plus 10 is 14. 9.3 plus 4.7 is 14. But take a look at the strengths of the conjugate acid. We notice that this is has a very weak conjugate acid, while this one has a stronger conjugate acid. Now you can see this by the relative size of the pKa. The lower the pKa, the stronger the acid. Now the reason for this is because of the greater negative charge here. It is less likely to give up its H+. So this one here, because of the less available negative charge on the nitrogen, will more likely give up its H+, and therefore we get a stronger conjugate acid in the case of aniline. The other thing we notice is that we can do what we were doing with the acids earlier. We can add electron withdrawing and electron donating groups to the ring, and we can investigate both the basicity and the strength of the conjugate acids that we get. So if we take a look at aniline, we can see that the pKb is 9.3 and that the pKa of the conjugate acid is going to be 4.7. So we've got a 9.3 and 4.7. In the case of adding a nitro group, you can see what effect that has to the pKb. The nitro group makes the aniline less basic. As you see, 9.3 to 13.0, the pKb has gone up. Now the reason for this is because the nitro group is going to be sucking electrons out of the ring. If it's sucking electrons out of the ring, it's sucking this lone pair of electrons away from the nitrogen as well. And that makes this nitrogen less basic, less able to grab onto that H+. This produces a conjugate acid, but the conjugate acid is going to be fairly strong, again, because of the lone pair on this nitrogen being sucked into the ring. It's less able to hold on to any H+ that it actually does grab. And again, you can see the sum is 13 plus 1 is 14. Looking at the effect of adding an electron donating group, we can see that the electron donating group will make the aniline more basic, 9.3 down to 8.8. And that's because we're pushing electrons into the ring. That means we're kind of pushing more electrons onto this nitrogen as well, making it more able to grab an H+. As you can see though, it also weakens the conjugate acid, and that's because now it can hold on to an H+ a bit better because of the greater electron density in the ring, and therefore it weakens the conjugate acid relative to what we see with aniline. I'd also like to talk about the basicity of some aromatic compounds. If we take a look at something like pyrrole, as you can see with pyrrole, the a lone pair on the nitrogen is actually involved in the aromatic ring. Remember, it takes 6 pi electrons, and these 2 electrons on the nitrogen are actually part of the pi system. That means that it's going to be pretty difficult for these to grab an H+, and you can see that's reflected in the basicity. The pKb is actually 14, and the pK of the conjugate acid is a very strong conjugate acid. It would love to get rid of that H+, and the reason it would do that is so it can become aromatic again. So we've got a very low basicity here because the electrons on the nitrogen are involved in the aromatic system. If we compare that to pyridine, though, you can see that the nitrogen here does have a lone pair, but these electrons are not involved in the aromatic system. This already has 6 pi electrons in the aromatic system, so it is a whole lot more basic than pyrrole is. So these electrons are available to take the H+, and we get a pKb of 8.8, so it's a lot more basic. And we have a conjugate acid here that is going to be a lot weaker, and that's because this is going to be less likely to get rid of the H+ because of the greater electron density on the nitrogen due to the fact that these electrons are not involved in the aromatic system.